go through the short introduction about myself. Then I go through the terms, embedded software and the testing. And then I go through the standards, and then I go to the main core of this presentation about the challenges and test cases related to the embedded software system. Here is a short history about myself. The both are only the important parts. So I start by the network administrator in 2000, and then I go through the hardware designing. And I follow with a master degree at the Faculty of Electrical Engineering at Czech Technical University in Prague. And then I was also a member of IET, the committee member, and I was organizing a presentation for the students, but not for myself. And then I established a company, and I also doing, in parallel to the network administrator, I'm doing also flight software engineering. So it means software design on the satellites. Here is on the right side is a switch, which was manufactured from the industry. It is for higher temperature extension and with a protection for each port, but it is not important for this presentation. So currently, just to know about myself, just you can imagine what I can do or what is my skills. I don't know what's cursor. So I'm mostly related to the software developing, but in the embedded system, not in a computer, but also because I'm a network specialist, I also work in a desktop environment, but in a frame of network administration, not as a user active. So on the right side, there is a figure about a product for company which I did development over Linux. This is executed on Linux specially made for this network switch. It's 10 gigabit with the optics. And I also was interested or joined in the team of a PCB design because there are some issues, but this is not about today. Because I mentioned that I work for Solar Orbital. It is a spacecraft which was launched in February this year before the coronavirus, let's say, attack or come to Czech Republic. So we were quite stressed, many, let's say, many months or weeks it was covered off because also there was no operator in, or there was operator, but it was all the tasks delayed or postponed until the COVID situation will be better. But now it's even worse, so I don't know what will be in the future, but today we are presenting remotely. So here is only the link, because I think that you can take advance if you are interested. It is always a little bit difficult to find resources, so here are the links. So I will circulate it with Phil after the presentation, that you can click on it and check more details. So now back to the presentation itself. I will be speaking about the embedded software testing. So I will first describe what I mean by the embedded software and by the testing. If I say embedded, it is something like if you are executing software, which is, for example, it is shown on a figure on this. Oh, sorry, I'm looking at the monitor. This one, if you look at this hardware, it is like this, just to compare the size. So I'm a specialist who work with this embedded programming of such devices, not exactly Raspberry, which you can probably identify, but you can develop any software on it from scratch. So you can create new drivers. So this I call embedded. And in embedded, generally, you have two options. One is to use, and it depends on the memory which is available, because when is the budget like this, related to the safety critical, which can be used because I'm in a section of automotive, medical, aerospace industry. So I don't know who is watching us. So speaking generally safety, I mean application which is somehow critical for the users itself. Just an example, My first device, which I developed on the embedded software or such device, was a humidity measurement, but this was not used for the weather condition. It was used to start snow making by the team in the mountains. So I was quite surprised they use it as a, let's say, nominal input, because it was from low-cost components, I should say. And if there will be a mistake in the measurement, it can be in the cost something like 10,000 euros, let's say, fail. So safety critical, it's sometimes hard to specify. So being simple and using, for example, the definition by IEEE, it can be understood as a software that you will be executing in an environment or in a system which can result in unacceptable risk. And what can be the unacceptable risk? Here are some, let's say, cases just to check if you understand what is the risk. So, for example, in space segment, if you have an instrument and only the launch costs so high that is much more than my salary, let's say. So it's important to not have a risk like that you execute there any command remotely, and based on the execution you will lose such instruments. So it's, let's say, an unacceptable risk. Additional one in aerospace, for example, I'm doing also software for UAV. It means aircraft which are controlled from the UAV. It means aircraft which are controlled from the ground. Is this very similar? So if you lose a communication link, it can lose also the UAV, because you are not sitting inside the UAV and you need a fully functional communication link. In automotive, it can be, I give only some simple example because I'm not a specialist in automotive, but I can, let's say, illustrate what I mean there as a risk. For example, very low risk, but still risk, that you are recording what is happening in front of your screen, and then if some accident occurs, you would like to see what was happening. For example, what happens, and if you lose the data only because, for example, the SD card was not working, it is quite high risk to do not have such video, because it can be lost what can be recorded on such devices. In the medical segment, I call everything segment because I use this terms from the space. So in the medical segment, it can be an example of a risk. It can be that you, for example, write software, and if you execute an instrument where a patient is X-rayed by the source, X-ray source, and if you change the power or if you set up a duration of such X-ray source, it can have an impact on a human being or patient. So it's very dangerous here. And in IoT, I have additional real example. For example, I do a power plant measurement. I mean output power, which are invoiced monthly to the distributor, and you need to be sure that the number of the energy which is used as the input to the invoice is correct, because if you make a mistake or an invalid number or even behind, by software testing, so I mean by the embedded safety critical software testing, we can see several tasks which can be done at the unit level, integration level. And if you're saying testing, you need to define where you would like to exactly test. So I would like to not go into the details, but I would like to point you to some of the interesting points. And testing is not always about the software itself, meaning, okay, so I need to check every 10 minutes. So it's good timing. By the technical testing or verification, because there are two cases, especially different in America and in Europe, but I think also between the industries. So if I'm speaking about the verification, I mean technical specific verification of technical specification. It means requirements. If I'm speaking about verification of software architecture design, I'm checking or verifying if the architecture is complete based on the requirements. I'm also verifying code. So you see that the code is something which is very, let's say, not interesting from point of the verification, even it's important. But you can see that it's only one item of several testing or verification. And what I would like to, or also the documentation is important, but here I would like to increase your attention to validation segment or part. And what I mean validation, I mean validation against requirements. So even you write perfectly the software without any error in terms that is no bug inside, there will still be, let's say, invalid application that is doing something else what was requested by the customer. So customer specifies requirements as software developers, and you can see that there is also several procedures like validation of test specification, so it means validation of requirements, validation of procedures implementation, so it means how the test specification is implemented and test results and reports of such implementation. And altogether, it shall be also, there should be traceability between the test specification and requirements. Only shortly, I will go through the standards and then I go into the core of this presentation. So don't be stressed that I talk too generic until now, but I think it's good to synchronize each other to that we know that we are that you will be sure what I'm talking about. Because I'm from the flight software segment or space segment, I'm using this following standards. It is available for the after the registration, so feel free to register at website of ECC and ECSS, and you can download any of this standard. You can check it, but it's difficult reading, so I only recommend to start by this handbook, which is a little bit also difficult reading, but if you are doing testing, start point, and then you understand also the additional standards around this this book. So from space segment, I recommend this handbook. From aviation, but I need to indicate that I'm not specialist in aviation, but I know that it exists, and there is also important the safety critical software. I mean autopilot, especially for UAV. So I can recommend this standard, but it needs to be purchased. And maybe instead of standards, I recommend these books, which is mostly related to the requirements instead of software development in terms of how the function shall be implemented. So it is the topic which I would like to describe today, more about the requirements or what can be mistakes in the design, not by invalid writing of the code or incorrect interpretation, but invalid requirements, let's say. And from automotive, because I'm not specialist, I cannot say how many standards they use, but for sure at least the coding standard for coding, and especially for the C, because in embedded system, it is typically used C instead of C++. Here are the list of the programming language. This is coming from the aerospace segment. So one of the primary language are C or Ada. Assembly, but only for the initial procedures of CPU, bootloader, and so on. And in let's say later stage of the code, it is used as C or Ada. There are also other languages like C++ or C#, Java, or the oldest one, Fortran, Pascal, but it is no more used now. But the C++ is so reduced in terms of what you can write there that is like C. And my recommendation or my view of how to use the coding standard is to use of the programming language only what is really needed. So don't use all the techniques which are provided by the software or by the language, and use only what is important for your project or for the testing needs or capabilities. Regarding the criticality categories levels, which are defined by, let's say, two standards. For example, for space segment, it is criticality categories, and for aviation software, it is a level. But you can see, I put it here in one just to see the differences. It looks almost the same, that is ABCD in both segments, but there are different, let's say, nomenclatures, like that you are using requirement baseline technical specification for the requirements. In aviation, you use low-level requirement, high-level requirements. And what is important that at the level B or E, also for the criticality B or E, you need to have independent software verification and validation. So additional company which is not held by the same owner to check the processes, how the software is developed, not only the software itself, but also the processes that you verify the inputs, verify the outputs, validate the requirements, and so on. Just an example, in the solar orbiter, which I showed at the beginning, there was on one instrument, there was two software, one, let's say, bootloader, which you know from computer, like something which is executed before operating system. So it was criticality B because it was loaded in the read-only memory, and there was additional criticality C, our nominal application, which is executed on the spacecraft. So on the spacecraft, you are closely between B and C. And if you do, for example, rocket, what doesn't mean rocket, but it means if you do something which is very essential for the missions, like engine or something like that, you need to have a criticality A, which is the top of the design in the software. So now I move the mouse just to not shut down the presentation by the power optimization. Now, what are the challenges in test cases? Because I said that you have two possibilities in an embedded system. You can use your own software from the scratch, from the beginning, or you can use some already existing software. So if I'm speaking last one, the last item in the sequence, and before the operating system is loaded, there is also bootloader and bootstrap. So the challenges is here, how long you can wait until the IoT, if you, for example, use Linux operating system in an IoT, how long you can wait until IoT device is ready, your application, really what you need from the device. And my question is, who is responsible for such a Linux operating system? Because you do probably the application, right? This is your business, the application, not the operating system itself. You would like just to use the utilities of the operating system. So who is responsible? I shall answer that only you. And be aware that, for example, bootloader, which is the first program which can be executed on the hardware, is written by the manufacturer of the chip component. And even you have, for example, I have several NDAs, but still I have no access to the source code. I have only how it is working, but I cannot review the code. So if I will be responsible for such device, for example, in medicine, I need somehow to cooperate with the manufacturer of such component. Or I can't validate such software. And there's also additional segments or software items like Bootstrap or Microboot, which is doing loading the kernel or root file system, which is the essential part of a Linux operating system. Second, what was changed in the embedded in the last years is that previously, I will show it in the next slide, but today, if you are developing embedded system for the Linux, you are using external volatile memories. It means that you have executed, of course, you have application outside of the chip. So it means anybody has access to such chip. So he can replace Bootstrap, Microboot, kernel, root file system, including your application. And also, code is executing external RAM. So he has access to anything which is inside application. So if you would like to debug or identify some secret information, it is very easily to find it because it's an external component. So what is the changes? Previously, the application code and data was shared on the same chip with the CPU. So it means that until you, let's say, you need much more higher, let's say, skills, and you need a lot of tools to, let's say, open such application. It's almost impossible. And the second is that you can erase and reprogram such application. And everything what is written or what was written when this was in history is that application today it's outside of such chip. So today it is not possible. It is the challenges which I write here as a bold one, that any code can be executed on the target hardware. So even I'm responsible for developing any device like this, and I put the code inside, it is still possible that somebody comes, remove the data, put additional application, execute on my hardware something different. And as a user, I need to be sure that I'm using the hardware device properly or embedded system properly. So there is additional text, some additional techniques like secure boot, but it's absolutely changed how was secured before, because before it was secured by the, let's say, by design. So it was code was loaded inside the chip. So only possibilities you have only to erase such software and load there something else, but or lock it to do not erase it no more. But today the data are stored outside of the chip, so you need to somehow encrypt them. And the question is, if you would like, because you have only one possibility is to program the key for decryption of such software. So you need to check if you would like to have a common or unique security key per device. So it means if per device will be unique external application, it means external image which can be uploaded by the user provided to you to the website. So if you imagine if you have a million of the instruments, you would like to do not have many images for each user uniquely. So probably you will use a common key in general, but it's up to you. So this is new challenges, which was not, I worked in embedded for several 20 years, let's say, and this is something new today. So it's not a topic which was discussed previously. And I go more closely to, because I don't know how you are a specialist in the embedded system, so I go a little bit higher, which you already know, that non-volatile memories today is implemented only by two technologies, NAND or NOR. NOR is too small, let's say, to have, or it's not as small as needed by a Linux operating system, so it can be still executed in Linux operating system. But the trend is that only NAND technologies is used because it has large capacity in contrast to NOR. And also, only the difference is that the NOR can be executed directly from the CPU. So I can execute the code, which is located on the memory, directly without any preprocessing or uploading to the memory and then executing. How it is implemented, this is by the NAND chip, the NAND technology, and you have two options in embedded, eMCC chip or micro SD card, as you like, but it is almost the same, or flash chip, which guarantees how the component works, because in micro SD card there is some wear leveling which can hide some functionality which we would like to have, for example, control about it. I need to check the timing. I have more 10 minutes, so more 10 slides. So I go through the NAND flash chip because this is what is used inside the CPU or close to the embedded system. What is there different from nominal approach is that there are blocks. Each block contains many pages, and each page contains something like out-of-band information, where you can store, for example, ECC correction to recover the information. Why is this? Because today the approach is that you have even if you purchase new component, there still be existing, let's say, failures in such chip. So there is already backlog, and they can occur also during the execution of software. So my question or challenges here are, who is checking the ECSC if it's inside the chip, if you're verifying it? Because if you are executing at the laboratory, it is working. But if it's in real application, you need to check if it's done by the component itself, so you need to stress if it's done by the operating system, or if you should be responsible for such handling of, let's say, ECCC. And there is additional topics which need to be discussed, is to have, or I provide you an example. You can write to the sectors only for, let's say, read-write operation, and you have different sectors. Then you have only for the reading. And what can happen? Then if you write to the sectors which are not for the reading, it still can be corrupted, such sectors. So even you writing to different sectors, your sector reserved only for the reading can be damaged. And also, which is, let's say, a little bit strange, but it's true, that only reading can cause also the data corruption. So it is not only the writing process, it is also about reading. So here is what we are fighting with. So at the beginning, when the technology starts, it was something like that we can do programming 100 times. Today, it's as low as 500. So you need to be very careful if you are certain the NAND chip, which kind of, let's say, technology is produced such chip. Typically, the NAND chip, because it's placed in the embedded system, they use the, let's say, high-end technology, but I don't say that. I would like to not say high-end. I would like to say the most, let's say, endurance and durability of such component. So here is, again, additional challenges. That how many times you can update such application, and what will happen if your bootloader will be damaged because you are updating applications, you are not touching the bootloader, but still it can be damaged because how the NAND flash chip works. And also I give you in a presentation that I will be talking about the logical errors. I just address several, and that's all for my presentation. So we are very close to the end. What I mean, the integration testing, by the definition, it is something where you do software items testing. It means each component connected together with each other, and you are testing how they interact. And also that you would like to ensure that the interaction between the software and the hardware, here is called external interfaces, it's working properly, but not properly in terms that you are executing as documented, but with how you define the functionality. So in space especially, you are designing software when hardware is not available. So this is, you need to develop a software without any execution on the hardware, on the target hardware, which is flying. But you can use some additional techniques like engineering model and so on, which is not today's topic. Just to compare, if you are integrating at the software level, so this is what is defined here, which is, let's say, nominal approach, but also at the system level, where you would like to verify requirements, because requirements sometimes text only, and you need to verify them also if there is no something like logical errors, which I would like to address now. And what are the logical errors? It's not caused by the implementation. So it means the code is perfect. It's as recommended by the requirements or guided requirements. And the problem is that it's not covered by the requirements because you miss some logical aspect, like you do not know that this problem exists, so you do not add additional requirements to customer and saying, okay, this can happen, so let's add additional requirements, because additional requirements mean additional costs. So this is the main approach which you would like to do not do, but it still exists. Just example, which happens in logistics, for example. I was developing hardware, including software and the hardware items. I connect everything together. It was serial number well identified. Each hardware item was identified by the number which is visible to the user, but still happens that at the end of the process, the final deliveries, or how to say, reseller or provided to the end user was exchanging the box. So what was written in the box was not true what was inside. I know that this can be tested also, but everything was fine until you discovered that the users are different of such device. So it was not the serial number exactly matching the user, because it was in project where was needed to have anonymous of the users. So you cannot link between them. You cannot ask user to enter details of their devices, and this happens. So it was it is software error, or it is hardware error, or it is process error, or it is a missing maybe that you are running a product in different country, that you do not block it. For example, that you, for example, in Russia, that you cannot have encryption, strong encryption, or maybe some simple example. If you have Wi-Fi, you have some limitation on power output or frequency usage, so you cannot select. Even if you have a valid software, you still need to know in which country are executed. Same for the compatibility, like in the computer science. If you are using a laptop, for sure the hardware producer is not testing all the equipment and all the accessories which you are able to connect to such device. So there can be a problem of compatibilities, and also some penetration issues, like that that is entering to the device invalid data which you are not expecting during the design. Here is only several aspects, last 3 slides, and then we finish. That even you designing perfectly, you're writing correct software, you do validation, there can be still errors. And in the chip inside, so you should check error data before designing. Just examples. Microcontroller can have 2 buses. You are designing 2 buses, but then you indicate during the manufacturer that there is a bug on the chip, and workaround is that you can use only 1 bus. So at this moment, you need to change the hardware or change the requirement, but for sure you are in trouble. But not your fault that you are bad software engineer, but you did something in the process wrongly, or that you have not updated the error data sheet. Second case can be that, for example, microcontroller can have encryption unit, and the encryption unit provides incorrect values, which is a bug, but which you do not identify, for example, during the testing, and workaround is none. So it means that you cannot use it no more. So if you are expecting that you will save a CPU load for application design, again, you need the hardware to be redesigned and requirements to be changed, or something like that. Additionally, which is a little bit difficult, which is not like easy, I mentioned before, is, for example, data cache. Because today, the manufacturers of the chip, they place a lot of components together, which are probably not well tested, but doesn't matter how it happens. But in ARM processor, typically in the embedded system, you have only 1 core. Today, it is extending. It is 2, 3, and 4, maybe additional 1, but the 4 are the best one. Because you have a trouble with the heating, and probably the embedded system should be without ventilator and so on, or air conditioning. So this is the reason why there is only 1 CPU and not so fast as in computers, no one. And what happens here, that you have CPU, you have Ethernet device, which was receiving data, but the data was transmitting or transferring to memory by the DMA channel. So it was not going for the CPU. And when the, for example, packet was received, it was in the memory, but the CPU has no indication that the memory was changed. So if you make a mistake, for example, like here happens that I have this later mentioned, but it is that the data cache was enabled by the external library. So you do not know that it was enabled. And what works, it was used this library by the other team than the designer of such functionality. So who was designing Ethernet connection, who was not aware about this data cache, and even it works perfectly from point of the logical point of view. Okay, you are reading data, fine, but you need to erase data or invalidate the data cache items. So what is the result? That the test you can execute successfully if you are focusing on this transfer. But if you are running application in nominal condition, there can be duplicity in the data, incorrect values, frame drops, and everything. And any change in code that you make very different behavior. So it's very hard to define or to identify when you are doing such application to find out what is the error. And last one is here memory scrambling, which you probably know from the computer when you have ECC memories, probably in the servers. You use it for, let's say, testing that there is no invalid bit in the memory. But let's take this example. If you have a airbag in car, you know that probably the application which executes such code is never executed only once. And because it's not executed, you cannot discover that there is a error correction error. And when it's executed, it's too late to fix that such bug. So it's important to do memory scrubbing during the execution of code, even you are not using such code, and especially for non-volatile memories, which can be damaged also only by the reading, not by the writing, but also by the reading. So it's important to do memory scrubbing in an embedded system. Okay, another one, purchasing the components. If you purchase component in embedded, it's sometimes issues, not like in the computer, that you can wait 25 weeks, which is no problem. I mean that if you order or place order, you can wait additional 50 weeks until you receive such amount of components. So it's very difficult to handle this. And what's happening in the history, or what happens to me at least, is that even the component was purchased from the official distributor, the component was still unofficial, or mean it was somehow corrected. But what was, even you are able to read all the registers from the device, it looks perfect, but the component was not functional. So you need to check not only the process of purchasing, but also if what you purchased, it is really working. For example, with the computers, if I'm buying a hard drive, I'm also doing, for example, initial for arrays, just to be sure that I'm able to access all the sectors instead of doing in the real situation. So before attaching the, for example, disk drive to the network storage. And the errors cannot be not only technical, it can be also logical. Just to have some fun, it can be something like this, that you have requirements that the device should support 1 GB SD card, which was written in a time when it was, let's say, quite far 1 GB. But today, if you are using the product, you are unable to use it because you are unable to purchase such low capacity SD card, and so on and so on. I will keep it with all this. So my conclusion or my output from this presentation, which you can use for yourself, I have here the books. So this is the handbook from ECSS standards. So it's quite small. This is the book which I recommend to you about the requirements. It's quite nice, but it's very difficult reading, but I recommend to you. And MISRA standard I have no here, but if this is, let's say, in the dimension of number pages like this. And the challenges today in embedded is that we move from the writing the code from the scratch. We are going from modeling, which you already know from the business, but from the embedded until today, or let's say several years ago, it was still written from the scratch. So again, you are writing a function again, because you are writing in this C, not C++. So all the modeling tools, which are for the Java, C++, are not well functional for the C implementation only. And what I would like to, let's say, suggest or recommend, or it's a strong word, so only suggest, to test not only that you do not need to test software itself, but you need to test always the requirements. And I will show you this tomorrow by this workshop. So you can attend also, there is some additional places available, so you can still join. And I will show you on Linux how to test some unit test, but you need to have some skills in the software development. But also I can adapt the presentation or the workshop based on the capabilities of the attendees. So thank you very much. Now I'm ready to answer your question. I have in front of the table so I can also draw.
So Peter, thanks very much. That was very interesting, even though I'm not technical, as I told you before. But for me, it's an insight into a world I know almost nothing about. So always very fascinating for me. I hope some of the other people are probably, hopefully, more technical than me, because I'm very untechnical. There's 3 questions. First one from Pepper, but I think you mentioned some things. What sort of skills and tools do you need to know to be able to get into embedded software testing? Taking from the point of view, you're I don't want to use this word badly, standard software tester who would be interested in getting into embedded software testing. What sort of things do I need to work on in order to be able to do it?
You can use, for unit testing, you can use existing tools like vectors. It's mentioned in the presentation. It's probably somewhere there, the links. The vector cast, Cantata, probably you know from the normal computer science. So this tools is also available. The modeling also, there is some like Magic Draw, which can be with plugin for C, not C++, but C. So these two exist. It's up to you if you would like, if you are, let's say, if you are beginning. So this is point of my presentation, that even you produce perfect software, you still can have additional issues. Like if you use Linux operating system, you need to validate, which is, let's say, strange until today, because until today you are writing everything from the beginning. So you are responsible for loading the image, verifying, executing first instruction. In the computer, you verifying when you execute all the application, or you let's say verifying the complete system, that the storage is complete and so on. And the embedded world, you can look at the computer. So if I, for example, exchange something in your computer, how you identify, okay, today is possible in the computers, there is a chip that you can verify that the bootloader is really Windows, and it is not, let's say, adapted to some users or to some functionality which can be externally modified. But there is additional issues. Just imagine you are installing antivirus. Antivirus has access to everything in your computer. But are you verifying that this antivirus is not accessing security information? Well, this is the question like in embedded. So I'm installing something where is executed a code, which is not mine. So I can never verify it. I can only verify it from, let's say, as a black box. Okay, it is working, it's fine. What I can say, I hope it is somewhere in public that I see a code, which there is some technical issue. No, probably this is under NDA, so I cannot say it, but there is some errors for sure, as always in the software, and it's illogical. It's not like that we write incorrectly the function or the manufacturer, but there is something which in some combination do a security error. And this is important, that you are verifying against requirements. And the customer is not specifying, he's asking you also to prepare the requirements. So still you are responsible for overall software. And this is my aim of the presentation. I would like to not go into the deep details, because I can find a lot of details, what is the problem. But today I'm able to test everything. I can, let's say, qualify by the proof of the concept, or how to say, by the dysfunctional. But I cannot guarantee if this will be instrument, for example, controlling my breath or heart, I will not use it. Not because it's not working, but because I'm absolutely sure that there will be at least one error which can cause damage. Yeah? And it is the same in the aircraft domain or avionics domain, and especially in aerospace or space domain where I work. And only today, I think that the computer science is much farther than the embedded, because embedded we do everything which is related to the software. So any peripheral, any devices, any components, so we know the knowledge. But the software engineer knows only the, let's say, his overview. So it is very hard to identify what is the possibilities? I have no solution. I cannot recommend you. I can only say, please educate the people. As much they know, they probably identify some issues. But of course, you do not need today. If I would like to certificate the Linux, I cannot go through all the code because some of the code is auto-generated, some of the code is assembly, and I don't know all the situation how the Linux works. So I have no possibility. It can be still working, but the issue is that I cannot guarantee. I cannot write that by the pen. I, as Petr Cesak, guarantee that this will always work because I have this margin for CPU load, I have this margin for interrupts. I can't. So I can use it as a system, and this is maybe the trend that because now the embedded systems is it is like normal mobile phone. Yeah, it is also embedded. So here is also what I update the firmware, and you are executing bank account application. And previously I have two phones, one for bank account, just to let's see the data here. So I need to be sure because here is not the software available for connecting to the internet. I show that the SMS is going only through the operator. So he is the last who can see the message. And any software bug here cannot, let's say, change it. Yeah? And even if I validate the application on the website, I still cannot guarantee that I didn't change the good software. Yeah? And this is, let's say, new topics which can be addressed, let's say, in the development, because I see in the car, you have a lot of cameras, a lot of systems, a lot of AI today, which are executed on powerful computers. So you cannot do it from the scratch. You need a lot of tools like encryption, communication, Wi-Fi connection, and these things. And you have no time to develop it. So you need to use already existing. But if you are using something existing which was not designed in the way that it will be in the future tested, because I don't know how in the computer science, in the embedded, or in the space especially, you have no hardware available until the end. So you are developing software, and you never execute all the combination of the software on the final hardware, not only because it's not available because of the manufacturing, but also because you cannot simulate all the inputs. You cannot say, for example, the solar orbital will go to the sun. You can calculate what will be the numbers of, let's say, power from the sun. But what will happen there, you cannot simulate on the ground. You can only simulate it differently on some different testing. So even if the mission is not successful, it means that it was not successful because there was an error in the software. It means that you have function A and you execute B. This not happens, but it happens that you have a logical errors. Maybe it's incorrect terms, but the message is that everything can be modeled. Like software can be started by that you create a model, how the state diagrams, creating the implementation, test codes. But what you can do until today is somehow requirement verification from point of what they are saying, because it's words typically or some diagrams, but it is still document. ISA, what started last several years, so you can, I have some slide behind maybe. ISA is doing modeling of a standards, so it means that there is no discrepancy between the requirements. For example, if one sentence says something, that there will be an additional one which will be against these requirements. So this is something which is, let's say, quite new. And in the near future, I think this will be the trend, that you will be not focusing on that you have perfect code because the tools are improving and you can execute them from or use them from the computer science and so on. But what is not done, I think, in details are these embedded, let's say, difficulties. Like, example, I have here a SD card. We use it as a logging machine. And I'm able to destroy such card, even there is 5-year guarantee, in 10 seconds. And what happens that it's not, let's say, touch the sectors which I'm writing. That when I'm reading, not only one byte, but several bytes are modified. So even there is ECC support, I'm unable to recover such error. So this is new challenges that it can happen that software which we execute many times again on embedded, you expect as in computer, when you restart, something helps. But in this, if you restart, it can also happen that it will never boot no more. So this is, let's say, something new, which is not an additional devices which are not using Linux. There is no problem because you have everything inside, everything is tested together, so you know all the environment. But today you are using CPU on one side, memories from the additional manufacturer. So also who is producing the chip is unable to test all the combination which you are using in your application. So it's still up to you. So you are still responsible. You are delivering, as I said, you deliver the last application which is executed, but you are still responsible what is doing the previous one. So if there is a bug, you need to find them. So this is what I'm doing today. So I'm doing the embedded software development. And what I just learned, I would like to show you tomorrow in the workshop. And I will adapt based on the attendees' skills, so I can be, let's say, simple or hard, as you like. So this is my, let's say, my output. And message is that there is many standards which are for free, which is not typical. So which you can, after registration, you can download, you can check them. I think it's difficult reading, but you can send me email, you can make additional presentation. And what I can say that every year I'm presenting on the Czech Technical University about the space software, but in general, but for 2 hours. So it's in more details than here. But I was not speaking about the space software, but just something which will be similar to the space in the future, because now it's CubeSat is used in the space, and there are developed like devices which you have at home, because the cost of the launch is very low. In contrast, if you are launching satellites like Solar Orbital, which costs so much that only the launch itself is much more than the salaries of all the development team. Yes, and this is the reason why the software is tested well, because you don't want to use such instrument. If you spend 5 years of developing, you would like to not see that first instruction is not executed. Yeah.
We saw Marian Suk's presentation 2 years ago, which suggested that sometimes the software testing in space is not so good, maybe, because there's some disasters he shared with us.
But as you see, it was not typical, let's say 10 years ago, that the manufacturer has a lot of error data in their chips. But today, because they are combining all the IP function and it's pressure of the, let's say, users, that they need everything, AI, I don't know what else, encryption, security. But the pressure to the developers is that you can have only one head who is designing the system. If you have many heads, it happens like that additional team is doing something else and they can go against, and it's difficult to identify such issues. Like today, I was preparing the presentation. I was connected at half hour before the presentation. Then I connect again, and I was unable to connect. 10 times I thought maybe it helps somehow. I don't know what happens differently. It happens, yeah. So even I am.
Okay, Peter. So I'll draw the presentation to a close. Thank you very much.
Thank you.